Let's talk a little bit about Lewis structures, which is a way that we describe bonding in covalent molecules. So for example, let's say we're going to draw a Lewis structure for F2, the fluorine molecule. To do so, we first notice that each fluorine atom, there's two of them, in the fluorine molecule has 1, 2, 3, 4, 5, 6, 7 valence electrons. So I'll draw one fluorine atom with 7 valence electrons, and then I'll draw a second fluorine atom with 7 valence electrons. And we notice that by having each fluorine atom share one electron with the other one, that each fluorine atom, if you count the electrons that are shared and the other electrons in the valence shell, if you do that for both fluorine atoms, both of the fluorine atoms feel, so to speak, as if they have 8 electrons in their valence shell. And this provides a basis for what we call the Octet Rule, is that atoms tend to share electrons until they achieve a stable octet of valence electrons. And in a sense, they do this to achieve the stable configuration of the nearest noble gas. Now, when we look at the various electrons in the valence shell of a molecule that's been drawn with a particular Lewis structure, we can look at two different types of electrons. There are going to be electrons that are involved in a bond, and they pair up to do so because they're shared. And any electrons that are involved in a bond, we call these a bond pair of electrons. So these two particular electrons here, this one and this one, these would be in what we call a bond pair of electrons. There are also other pairs of electrons that are not involved in the bond, such as this pair here, this pair here, and this pair here. And these we call lone pair electrons. Lone pair electrons are not involved in the bond. And with this basis, we're going to go ahead and describe a systematic way that we can draw a Lewis structure for any particular molecule that we choose. So I'll just quickly read these, and then we'll actually get some practice using these guidelines for drawing a Lewis structure. The first thing that you want to do is determine the central atom in a formula that you see. So for example, let's say we see the formula H2O, and we want to draw the Lewis structure for H2O. The first thing we're going to do is guess what the central atom is. And a central atom usually has several bonds coming off of it, and because of that, hydrogen's never going to be a central atom because hydrogen atoms tend to only want to make one bond so that they can achieve the stable configuration of its nearby noble gas helium. And it's kind of hard to be a central atom, with bonds shooting off everywhere if you can only form one bond. So in this particular molecule, we would pick oxygen as the central atom. The second step is we would determine the total number of valence electrons in the molecule or ion that we're trying to draw the Lewis structure for. So if we go back to water, we would count the number of valence electrons in all of the atoms involved in the molecule. So we would need to take into account oxygen, which has 1, 2, 3, 4, 5, 6 valence electrons. And then we have 2 hydrogen atoms, and each hydrogen atom is going to provide 1 valence electron. So it's going to be 2 times 1. And we'll add those up for a total of 8 valence electrons. And we've taken care of the second step. We've determined the total number of valence electrons in water. Now we begin drawing the Lewis structure. And to do so, we're going to draw single bonds from all the terminal atoms to the central atom. So here's how we do this. We've determined that oxygen is the central atom, so we're going to write that in the middle. And now we have 2 hydrogens to which we're going to draw single bonds. So we're drawing single bonds from the central atom to the 2 terminal atoms, which in this case are hydrogen atoms. So that's that step. Now we go to step number 4. We're going to give each terminal atom an octet of electrons, but of course we're not going to do that for hydrogen because hydrogen only needs 2 electrons to fill the first subshell or the 1s subshell, or the entire first shell. However, in other atoms, we're going to need to give 8 electrons to, just not in this particular case. So this is taken care of because we do not need to give, obviously, hydrogen 8 valence electrons. Now we go to the next step. We're going to place remaining valence electrons on the central atom. Well, what does that mean? Well, we've used, let's see how many electrons we've used. So if you notice, each bond here, I didn't draw in the electrons, I should probably do that. So I'm going to draw in the 2 electrons involved in each bond. And we have a total of 8 electrons we need to count for, 8 valence electrons we need to count for the H2 and the O. And notice we've used up 1, 2, 3, 4. So there's going to be 4 that have used up of the 8. That means there's 4 left over. And that's what this step 5 means, why we're going to place the remaining valence electrons on the central atom. So to do step 5, we have to figure out how many electrons we used up in making the bonds, and subtract that number from the total that we need to use. We need to use 8. We've used up 4 to make these 2 bonds, and there's a total of 4 left over. And those 4 that are left over, those are remaining, and they go on the central atom. And so I'm going to place those in lone pairs around the central atom like this. So notice I put 1 lone pair up here and 1 lone pair down here. Now that we've taken care of this particular step, we move on to step 6. If the central atom has less than 8 valence electrons, we're going to move a lone pair from a terminal atom into a bond pair with the central atom. So let's check our central atom. We're going to check how many valence electrons it has, including shared electrons. So let's see, this hydrogen feels like it has 2. This hydrogen feels like it has 2. And oxygen, if we count all of those, it's going to feel like it has 1, 2 in this bond, 3, 4 in this other bond pair, 5, 6 if we add in this lone pair, 7, 8 if we add in this lone pair. And so we see that all atoms are satisfied. Oxygen has 8 valence electrons, and each hydrogen has 2. And so we don't need to move on and repeat this. We don't even need to do this step. And so at this point, the Lewis structure is drawn for water, which we could write our oxygen, single bonded to a hydrogen over here, single bonded to another hydrogen over here, and 2 different lone pairs around the central atom. Let's try this for a couple of other molecules. Let's start with carbon tetrachloride, CCl4. So first we'll determine the central atom. Very often the central atom is going to be the atom that's listed first in the compound. So we're going to have carbon be our central atom. The next thing we want to do is to determine the total number of valence electrons in the molecule or the ion. Well, here we have carbon tetrachloride, which means I have 1 carbon atom, which has 1, 2, 3, 4 valence electrons. And then for chlorine, I have 4 chlorine atoms. So it's going to be 4 times the number of valence electrons in chlorine. 1, 2, 3, 4, 5, 6, 7. So 4 times 1 carbon, that gives me 4. 4 times 7, that's 28. That's going to give me a total of 32 valence electrons that need to be used up. So the next thing we do is we're going to draw single bonds from all terminal atoms to my central atom. So okay, we're going to take our central carbon, and I'm going to draw a single bond to my first chlorine. I'm going to draw a single bond to my second chlorine. I'll draw a single bond to my third chlorine atom. And there's one more. We'll draw another single bond to my last chlorine atom. And I've taken care of this particular step. I've drawn single bonds from all my terminal atoms to the central atom. Now I move to step 4. I'm going to satisfy each terminal atom with a stable octet of electrons, except hydrogen. Well, here we're not dealing with hydrogen, so let's give each chlorine atom a stable octet. And we'll do that by adding 3 lone pairs for a total of 6 electrons to each chlorine atom. Because notice, we count both these electrons in the pair, 1, 2, 3, 4, 5, 6, 7, 8. That makes this chlorine atom feel like it has 8 electrons in its valence shell. We'll do the same thing here. It's got 8. We'll do it with this chlorine atom. And this chlorine atom. So that step's taken care of. We have satisfied each terminal atom with an octet of electrons. Now we move to step 5. We're going to need to figure out how many remaining electrons we have and then place them on the central atom. So how many valence electrons have we used? Well, each chlorine is surrounded by 8, right? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons around this chlorine, 8 electrons around this chlorine, 8 electrons around this chlorine, and 8 electrons around this chlorine. 8 times 4 is 32. That means there's none left over, and none go on the central atom. If that's the case, it should work out such that this carbon atom feels like it has 8 electrons in its valence shell, and indeed it does. If we count them, it's got 4 bonds, and each bond has 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And we've drawn the Lewis structure for carbon tetrachloride. We've already done this process for nitrogen, but let's just show you how we would write this out for the nitrogen molecule. So let's imagine I have N2, and I'm going to use this method, this guide for drawing Lewis structures, to end up drawing the Lewis structure for the nitrogen molecule. So first we're going to determine the central atom. Well, that seems kind of goofy. We just have 2 nitrogen atoms, so which one's going to be the central atom? Well, it's got to be a nitrogen atom. We'll just pick one of the 2. All right, so I'm going to have one of them be a central atom, and it turns out another one will be the terminal atom. Now we need to determine the total number of valence electrons in the nitrogen molecule. So we notice nitrogen is here on the periodic table. 1, 2, 3, 4, 5 valence electrons for each nitrogen atom. So let's see, for nitrogen, I have 2 nitrogen atoms times 5 valence electrons for each nitrogen atom. That's a total of 10 valence electrons. And we've taken care of step number 2. Now I'm going to draw a single bond from my terminal atom to the central atom. So I'm just going to take my central atom, draw a single bond to my terminal atom. Doesn't matter which one's which, it's going to work out either way. So let's see, I've taken care of that. Now I need to satisfy my terminal atom with an octet of electrons. So here's my terminal atom. Let's give it 1, 2, 3, 4, 5, 6 more electrons, and that'll make this feel like it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So we've used up 8. I'm going to subtract 8 from the total, and that means we have 2 left over. This is a step that students tend to forget to do. Don't forget to do this step. So once I've satisfied the terminal atom with a stable octet, I need to replace the 2 valence electrons remaining. We're going to go ahead and place those on the central atom. I'm going to put them right here as a lone pair. Now in this case, our central atom has less than 8 valence electrons. Let's look at this. It only has 4, right? 1, 2, 3, 4 is what it feels like. Remember, we count the ones that are being shared in addition to the lone pairs. So this needs 4 more electrons to get to 8. So what we do to make this central atom achieve the stable octet is we're going to move a lone pair of electrons from the terminal atom and put it into a bond pair with the central atom. So watch how this works. We're going to take this lone pair here, and we're going to move it, so to speak, into a bond pair like this. And now we're going to imagine these electrons aren't here. They're now in a pair of electrons, a bond pair. And we'll count one more time. 1, 2, 3, 4, 5, 6, 7, 8. This atom still feels like it has 8 electrons. Let's see how many the central atom feels like it has. 1, 2, 3, 4, 5, only 6. So we're still not done. We need to repeat step 6 until all atoms are satisfied. So we'll go back here to step 6, and we're going to continue moving lone pairs from that terminal atom into a bond pair with the central atom until all atoms feel like they have 8. So let's go ahead and move this this lone pair into a bond pair like that and count. Well, let's see. This atom feels like it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And sure enough, so does this one. 1, 2, 3, 4, 5, 6, 7, 8. And so we'd write the Lewis structure for N2, like I showed before in a previous video, to be 2 nitrogen atoms triply bonded with 1, 2, 3 bond pairs between each atom. And then it looks like this lone pair, we'll stick it on this nitrogen atom, and then this lone pair goes on this nitrogen atom, and in so doing, each nitrogen atom feels like, if we count the shared and lone pair electrons, each nitrogen atom feels like it has 8 electrons in its valence shell. Let's try this for one more molecule. We're going to do it for carbon dioxide, CO2. All right, first thing we have to do is find the central atom. And that central atom is almost always listed first, of course, unless it's a hydrogen atom. A hydrogen atom is never the central atom. Now we need to determine the total number of valence electrons in carbon dioxide. So let's see, I've got a carbon atom and I've got 2 oxygen atoms. The carbon atom is going to supply 1, 2, 3, 4 valence electrons. So 1 times 4. And then for oxygen, we have 2 of those, and each oxygen is going to supply 1, 2, 3, 4, 5, 6 valence electrons. That's going to be 2 times 6 for a total of 12. If we add those up, we're going to need to have 16 valence electrons in carbon dioxide. Now let's move to the third step. We're going to draw single bonds from the terminal oxygen atoms to the central carbon atom. So I'm going to draw my central carbon atom, and I'm going to draw a single bond from this carbon to this oxygen, and a single bond from this carbon to this oxygen. All right, that's step 3. Now I will satisfy each terminal oxygen atom with an octet of electrons. So this oxygen atom has 1, 2, 3, 4, 5, 6, 7, 8. We'll do the same for this oxygen atom. 1, 2, 3, 4, 5, 6, 7, 8. Now we will replace any remaining valence electrons on the central atom. Let's find out how many we've used. Well, 8 for each oxygen, right? So let's see, 8 and 8, that's 16. We've used them all up, so nothing goes on the central atom. Now we got to check our central atom and see if it has less than 8 valence electrons. If so, we'll move a lone pair from one of the oxygens into a bond pair with the carbon. Well, sure enough, our carbon feels like it has 1, 2, 3, 4. It needs more than that. So what we'll do at this point, I'm going to move this lone pair into a bond pair with my carbon atom. Now it still doesn't have its 8, the carbon still doesn't have 8 valence electrons. Watch, it's got 1, 2, 3, 4, 5, 6. It needs to have 8. Now in this case, there's 2 ways we can do it. And later on we'll learn how to tell the difference between which of the 2 is better. I can either move this lone pair, or any of these, into a bond pair with a carbon, so that I have a carbon doubly bonded to 2 different oxygens like this. Or I can take the same oxygen that's already doubly bonded and take one of its lone pairs and move it into a bond pair with the carbon atom. If that were to happen, I'd have a bonding system that looks like this. And so in this case, you'd have a carbon-oxygen triple bond and a carbon-oxygen single bond making carbon dioxide. And in this case, both oxygen atoms are doubly bonded to the carbon. This is the one that tends to be, not tends, this is what happens. So I'm going to move this lone pair into a bond pair with the carbon. And so what we see for the Lewis structure for carbon dioxide, we get each carbon doubly bonded to terminal oxygens. So each carbon makes 2 bond pairs with each oxygen, and then each oxygen has 2 lone pairs. And a simple way to think about why this is so is, in general, if you have identical oxygen atoms attacking if you have identical oxygen atoms chemically bonded to a carbon atom, in essence, you can't tell the difference between them. I mean, they are absolutely identical. And so this would refer to those oxygen atoms in an identical fashion where you really can't tell the difference between one or the other because they're both doubly bonded. Whereas if the bonding was done in this case, then there would be a difference between the oxygen atoms, in which you would see this one to be triply bonded to the carbon and this one singly bonded. Here you could tell the difference between the oxygen atoms. And chemistry doesn't tend to work out that way. It tends to work that if things are in identical environments, then they're going to act identically.